Okay, good morning. I think we can start. So the first speaker is Hiranya Peiris, and she's going to tell us about pixels to physics, the promise and challenges of survey cosmology.
Thanks. Good morning, everybody. Thanks for being in here in the first sunny day of the conference. And thanks very much for the organizers for such a nice meeting and such exciting science that we've heard about. So I want to start a session which I think is more observational than what's gone before. And in particular, I want to tell you about the promise and also the challenges of survey cosmology as we start the next generation surveys. Okay, so after the Planck 2018 release, it's very clear that the signatures of new physics beyond the standard model of cosmology, the lambda CDM model, are quite small as imprinted in the CMB. So I want to start with the framing of the situation we're currently in, which is that we're living under a standard model. Is there a pointer thing here? Is it this one? Okay, good. So the standard cosmological model is phenomenological, right? So it fits all the data we have extremely well, and it has been successful now for a couple of decades. And the issue is, though, that if you look at the ingredients of this model, it has at least three things beyond the standard model of particle physics. There's dark matter, there's dark energy, there's a mechanism for the origin of cosmic structure, such as inflation, that we need to put in there. And these are phenomenological models, and we need to understand the fundamental physics behind these ingredients while also thinking about, have we got the whole picture right? Is this model right in the first place? And in thinking about this problem on how to make progress towards a paradigm shift, I wanted to bring up this idea, which I think is attributed to John Wheeler. There are two ways to make progress. The first, which is called conservative radicalism, is to look at the underlying principles of the lambda CDM model, give up those principles one by one, and explore the consequences, how it changes with respect to the standard model, and then look for signatures of breaking those assumptions in cosmological data. So this must be done rigorously because principles are precious, and the underlying observables of the lambda CDM model have been tested very rigorously. So we have to beware of epicycles. The other approach is what would be called radical conservatism, okay? We've got a model, it's a phenomenological model, so let's take the predictions of that model very seriously, okay? So the lambda CDM model is a very predictive model, and you can look at its predictions in new regimes where we haven't tested it before and see whether the results we get are consistent with the predictions that we have based on fits to other cosmological observables. Okay, eventually it'll break. We know it's a phenomenological model. We know there's a lot to understand. And so this is how paradigm shifts in physics have typically happened. So there's a lot of activity in the field in both of these two approaches. And I'm mostly going to talk today about this one. So let's start with the nice picture of cosmic consistency that we have now. Okay, so Eiichiro very nicely outlined yesterday the success of the primary CMB, the temperature polarization, the polarization power spectra. Okay, so when you fit the lambda CDM model to those observables and then you make a prediction for the CMB lensing, you get this black curve. Then you actually go and measure and reconstruct the CMB lensing. And you can do that from both Planck and also these nice ground-based experiments, SPT, ACTPol, and SPT-SZ's surveys are shown there. And there's a nice picture of consistency. So a fit to independent data matches what we observe in a new observable. And this picture continues when you look at this updated version of, I think we've seen the 2004 version of this plot in Kentaro Nagamine's talk on Monday, where these individual observables basically spanned different wave number ranges back in 2004. We have now many probes probing the same wavelengths, and So this is a summarization of the constraints on the matter-power spectrum from all these surveys, and it spans 14 gigayears in time and 3 decades in scale. And there's again a nice picture of consistency with multiple probes overlapping in different decades of wave number. So do we see hints of this thing breaking? So Jody very nicely pointed out that we should not jump every time you see a 2 sigma result. And in cosmology, we don't have any 5 sigma tensions, so we don't even have that. We are just looking for things where this lack of consistency starts to make us uncomfortable in some way. And that's when they creep towards and above 3 sigma. So this is not a hint of the model breaking. It's to explore where the model could potentially be extended. And when we look at this plot, this is a plot summarizing the growth of structure, so it's matter density and the amplitude of fluctuations. This is, again, the fit to the primary CMB over here. And this was from the cosmic shear data set of the kids survey. And if you look at this plot, you start to see that at the 95% joint constraint, these constraints don't really overlap. And people looked at this, and this sort of thing is called a tension in cosmology. So people got interested about this tension. So is this a hint that the model is not working? So then we get a new survey, the DES Y1 release. And this analysis, which I'm not going to really discuss because I think Risa is about to discuss it in her talk, I just want to point out that the overlap between these contours and these contours is slightly better than in the previous plot. And so this indicated perhaps that there's something to be understood. And so people revisited the analysis assumptions that had been made when looking at this cosmic shear data. So it turns out that if you update the treatment of the shape noise and also what's called the multiplicative shear calibration uncertainty in cosmic shear analyses, it both improves the internal, chi-square per degree of freedom for the data set itself, but also shifts these contours up a bit. Okay, so you can see that these contours, the original contours, with the updated analysis, now overlap better with this set of Planck contours. So this idea of overlap is very vague so far, as I've been discussing it. Is this level of overlap an indication of tension? So to do that, you have to have a proper statistical basis for understanding what is this tension and when we should trigger ourselves to look further. But when you then look at the dark energy survey cosmic shear constraints and the kids survey here, you see now they overlap extremely well. So without defining a statistical basis for saying things are consistent, can anyone, do people look at this plot and say that these data sets are consistent? Do they feel like they match? Hands up. Okay, all right. Well, I think it's a bit suspicious, right? Because they're independent data sets, and they overlap extremely well. That's got to be a coincidence. But yeah, so this is the sort of thing that I want to get at in a more rigorous way in the next part of the talk. So going back to CMB lensing, so in this plot, we can see the DES lensing contours over here, the Planck CMB lensing contours over here, and the combination. This strange shape in these contours comes from marginalizing over an extra parameter called intrinsic alignments. And so you should ignore that a little bit. But these contours and the prediction from the primary CMB in this plane is indicated in that level of overlap there. So there's a question mark after this word consistency here. So this is something that we have to keep watching. So moving on to a different observable. Now this is, as a function of redshift, the standard ruler for the baryon acoustic oscillations, the co-moving angular diameter distance divided by the drag scale, relative to the prediction from the fit to Planck. And here, again, we see over a variety of redshifts and a variety of surveys, both spectroscopic and photometric, measuring the BAOs, that there's consistency except for this point out here, which is based on measurement of BAO from the Lyman alpha forest. So this is about a 2.5 sigma tension. And because the Lyman alpha forest is a less mature observable than some of these others, you might imagine that there are unaccounted systematics in that error bar. So when you turn that into an actual plot of the expansion history, so now this is the Hubble parameter, that's the local Hubble rate, and again as a function of redshift, you see these are the BAO measurements, these are quasars, that's the prediction from Planck for this expansion rate under the lambda CDM assumption. You see the local Hubble expansion rate measurements from the Cepheid distance ladder is significantly discrepant here. You can again see the Lyman alpha forest measurement as well. So this brings me to the controversy about the cosmological and distance ladder measurements for the Hubble constant. Okay, so if you look at a historical picture of this, we started out with huge discrepancies between different methods of measuring the Hubble constant, and eventually they converged in the mid-90s. And we started out the 2000s with very nice consistency between CMV measurements of the Hubble constant, which are not direct measurements, of course. They're fit to a cosmological model, which then predicts the Hubble parameter, and also the distance ladder measurements. So as the precision of CMB data improved, these started to diverge again. And here is a plot showing the publication year versus error bars from both distance ladder measurements and the CMB. And you can see that when the Planck release, the first Planck release came in, they started diverging and they have never actually converged again. This doesn't actually indicate an inconsistency between Planck and WMAP. If you restrict Planck to the multiple range that WMAP had high signal to noise over, they're completely consistent, but Planck adds quite a lot of extra data, and that shifts the value of the Hubble parameter in a way that's consistent with the amount of data that you have added. So does this indicate systematics, astrophysics, or new physics? So in my personal view, this is the most interesting tension we have in cosmology today, because both of these probes are very mature, and people have spent a lot of time analyzing their systematics and trying to understand and quantify those systematics and test for them. So in cosmology, when you see a tension at this level, maybe it's worth paying attention to. It's currently about a 3.5 sigma tension, and this exact sigma value changes based on what central values people look at, which particular data combinations people look at. It can go up to even 3.8 sigma based on that. Okay, so this is the latest on this. These are the traditional Cepheid distance ladder measurements in blue. There's WMAP measurements here, there's Planck, so we are now up to here, that's Planck 2018, and this hasn't really changed at all, and neither has the Cepheid distance ladder measurements, and the error bars have just tightened. This is the latest Hubble constant measurement from the standard Sirens in 2017, and that's a completely new cosmological probe. The error bar is still too big to arbitrate between these two other measurements. So now I want to put this on a possible statistically sound way of trying to evaluate what is tension and when we should pay attention. And it's based on this very nice work from Stephen Feeney and collaborators. So why should we care about the Hubble parameter? Well, it's a cosmological parameter that you can measure directly and locally with the assumption of a minimal physical model. So it's a very, very good way to try to test the overall consistency of the cosmological model, which is fitted to higher redshift data, but with much more physical and astrophysical assumptions. The simplest method to do this is to measure a robust distance and redshifts. And I'm going to talk about two different ways to use distance ladders, assuming a minimal cosmology. First, you anchor to nearby Cepheids with known distances to calibrate low redshift supernovae. The inverse distance ladder is the opposite. You don't anchor at low redshift, you anchor at very high redshift. You anchor to the CMB drag scale. And the drag scale measurement from the CMB is much, much less model dependent than assuming the full cosmological model and measuring the Hubble parameter that way. So it actually decouples high and low redshift information when you measure that. So then you use supernovae and BAOs to extrapolate forward in redshift. And so that's called the inverse distance ladder. The other way, of course, is to use CMB anisotropies and the full CMB likelihood, assuming a complete cosmology, and to then predict the Hubble parameter. So I want to propose the posterior predictive distribution as a way of assessing the soundness and the consistency of the model. And technically, this is basically a convolution of the likelihood of the new data with the posterior of the old. You make measurements of, say, a parameter or actually some function with some data set, and you predict what the new type of data should look like under that posterior. So then you can compare the measured values to this predicted posterior, which is the sampling distribution for the new data. And you say, are the new data consistent with being a draw from the model? And so this is model assessment. It doesn't need an alternative model or model comparison in order to make an assessment about the goodness of fit. It is essentially a likelihood ratio. And because we don't have a sound alternative model to lambda CDM, it actually has a very weak dependence on the prior. So that's also another nice property of this particular way of looking at it. So taking this way of quantifying tension, I'm going to just show you a one-parameter way of doing this, although that's not actually needed, but it's just easier to understand doing it that way. And all of the measurements of the Hubble constant can be compressed into a map estimate of a parameter, so that is the Hubble parameter here, but you could do this with any level lower in the analysis, predicting any observables that go into that data compression. So let's treat the Cepheid distance ladder H0 as the data. And so the posterior predictive distribution is the predicted sampling distribution of this quantity, given the Planck CMB data. So here's the Planck CMB posterior. This is the predicted distribution for the Cepheid distance ladder measurement, given the Planck CMB posterior. And then when you look at where it actually falls, it's way out in the tail, right? And I'm going to summarize the tension using the ratio of this value here to the peak. And that is just 1/45. People like to sometimes just turn this into a posterior predictive p-value. I'm not going to do that. It's fine to do it here because this is a nice convex distribution, but many PPDs are not convex like this. And some of them are also multi-valued. So using p-values is quite dangerous in this context. But anyway, let's quantify it with that ratio. So if you look at the standard Gaussian 3 sigma threshold in this context, that corresponds to 1/90. So the first thing you should take away from this is that when people say the Hubble tension is 3.5 sigma, they're making a Gaussian assumption, and that exaggerates the tension. Okay, these posteriors and the PPDs are not Gaussian. So those data sets, let's assume that 1/45 in the PPD ratio is something that we get uncomfortable about. Then we wonder, can other new data arbitrate this tension? And so we can look at the inverse distance ladder measurement. It does have this CMB information. It has the drag scale measurement. But as I said, that's very robust, and it doesn't use low redshift information. So if you anchor at high redshift and then use BAO BOS measurements and the latest Pantheon supernova sample to construct an inverse distance ladder. What you can see here is the CMB Planck posterior here. This is the inverse distance ladder posterior, and this is the Risa et al. Cepheid distance ladder measurement. Okay, so in making this inverse distance ladder measurement, we assume a smooth expansion history with a third order expansion of the Hubble parameter as is usually done. So that's that expansion. It of course fails at high redshift, but down here it's very insensitive to that assumed smooth history. So the first thing to note is that the inverse distance ladder H0 posterior agrees with Planck lambda CDM, and the two distance ladders are in significant tension. So again, we can quantify this tension. So this is the new posterior for the inverse distance ladder. This is the posterior predictive distribution for the Cepheid distance ladder given that posterior. And, and then there is the ratio from this point to that point. And it's a lower tension. Remember, the previous number was 1/45. Now it's 1/17. But it is still a tension. So the two distance ladder measurements are inconsistent, defined by this particular way of looking at it with the draw from the same model. But they both have, these two measurements have the supernova in common. So can we look at this with a completely new observable to arbitrate this tension? So I'm going to propose gravitational wave standard sirens to do that. So we looked at how well gravitational wave standard siren samples can arbitrate this tension, and to do that we simulated binary neutron star mergers with electromagnetic counterparts. So assume that you have a redshift measurement and you have localized it on the sky as well. We assumed 4 years of LIGO Virgo. This rate for BNS mergers is a little bit high, but consistent with the data. The waveforms were injected with colored noise, and it was analyzed with the same pipeline that's used to analyze the actual LIGO data. So each one of these posteriors actually requires about a few weeks of runtime. So we only have 51 detectable events that we have simulated. And when you look at it, so this is the luminosity distance posteriors for this sample. So they have kind of weird and funny shapes. So then, given this sample, we can compute the H0 posterior assuming perfect redshift measurements and Gaussian peculiar velocity likelihoods. And what I'm going to show you here is this is signal to noise. These are going to be the individual H0 posteriors from each one of these 51 samples, and this is the combined posterior. So it's going to play a movie now. And you can see as signal to noise rises, you start to measure H0 better and better, and you end up with this posterior. And you can see this was the underlying assumed value of H0 for that simulation. And you have made the measurement, and you can clearly see that it's shifted away from the true value, but we have sample variance. There's only 51 objects in this measurement. So we wanted to quantify this effect of sample variance and ensure that the analysis chain for this method was actually unbiased as well. And I'm going to show you that in a minute if I have time. But okay, so to arbitrate this tension using standard sirens, you can look at this plot first. These gray bars give an indication of the uncertainty from the standard siren method. And given the standard siren measurement, this is the PPD for the CMB data, and this is the PPD for the Cepheid distance ladder. So if the true value is Planck, and the so if you look at this over here, if the true value is Planck, then Planck is consistent with Planck, okay? And, but the Cepheid distance ladder measurement is way out here in the tail. So that's a PPD ratio of 1/300. So it can be excluded quite easily. If the true H0 is the CDL value, then CDL value is consistent with the Cepheid distance ladder measurement, but out here in this tail, the Planck measurement is inconsistent, but not as the level of the other way of doing it. Okay, that's because the Cepheid distance ladder uncertainty is much more than the Planck uncertainty. So it's harder to exclude the Planck value than the Cepheid distance ladder value. I'm going to move on because I have no time. 1 minute, okay. Anyway, ask me about the realization noise if you want later. But I want to also show you the possibilities of what we're going to get with BAO measurements. So this is DESI, which is coming in 2019, and it's going to make measurements of the expansion rate in all of these bins. So that's very exciting, and that's what we'll do to the inverse distance ladder measurement uncertainties over a wide redshift range. For standard candles, these are the prospects with ZTF and LSST. This is the sample I showed you in the current analyses, and these measurements are going to go out with very large samples to very high redshift as well. I'm going to end by saying that this is the survey that I'm most excited about. It's LSST. It's going to map both space and time in a way that expands that volume over 1,000 times over current surveys. And there is a collaboration called the Dark Energy Survey Collaboration, which is actually, the Dark Energy Science Collaboration, which is actually a combination of both cosmologists and particle physicists and computer scientists and statisticians trying to make sense of this data. And this is what LSST looks like as of this month, and it's also coming in 2019. I'm going to end there. Thank you.
Do we have questions? Yes, please.
So there was another paper of Stevens, I think, where he talked about the importance of the non-Gaussian errors in the local measurements, and actually they're like quite heavy tails on H naught. Right. Is that as important as the other methods you've been talking about? And are those errors included in what you've been doing now?
Yeah, these analysis I've showed you has that heavy-tailed method. It's actually using the full hierarchical model that Stephen constructed for the Cepheid distance ladder. The heavy tails are important in all of these measurements. And when we say an n sigma tension, as I mentioned, it's always pretty much overestimating the level of tension to what it actually is. So it's very important to look at it with the proper statistical method, like I showed.
Any more questions? Okay, please.
Could you go back to the slide where you showed two figures of sigma 8 tension, one larger, the other smaller? Yes, I think this is it. So the left one is neutrino mass fixed, and the right one is neutrino mass marginal.
Okay.
So what value of neutrino mass did you use in this?
So this is the standard way of doing cosmological analysis, where you fix it at 0.06.
Okay.
So most people, when they do lambda CDM analysis, fixed it there, and that has been the case since the first Planck release. But DES selected to marginalize over neutrino mass in what they call lambda CDM, which leads to strange elongations of these contours. Yeah.
Okay, thank you.
It would be good if we can all agree on what is lambda CDM. All right?
One more question here.
Related with the neutrino mass, I think it's important to how to assign neutrino to 3 species. How did you assign the neutrino mass?
So the, cosmology is basically sensitive well into the future, not to the hierarchy, but the sum. So
wait. But it depends on when the neutrino becomes, each species becomes non-relativistic. Is important, I think.
Sure. So I think the effective way of that manifesting in cosmological analysis is that n effective is 3.046. And that's the standard value that's adopted in all of these analyses. So it's a standard history.
But did you assume that one species could be could have the total mass of neutrinos?
It doesn't really matter, is what I'm trying to say. It's the sum that matters. The hierarchy doesn't matter for these analyses.
I don't understand, but yeah, actually, according to my experiences, that it depends on how assign.
So which observable are you talking about?
Low redshift observation is sensitive to the assignment, I think.
Low redshift observation. So you're talking about the inverse distance ladder?
Relatively, yeah.
Okay, so of course this depends on this n effective parameter. And when you look at, sorry, let's go forward to the inverse distance ladder. Right, when you look at this curve here, this is assuming a full cosmological model. So if n effective had not been assigned at the standard value of 3.046, this curve would change. And because the error bar that results on the drag scale that you anchor to will be much larger, you will see this flare out quite a bit as a function of redshift. This curve here makes no assumptions about neutrinos at all. It's just a third order expansion of the Hubble parameter. And so there's no assumption about neutrinos.
Okay, thank you.
Sure.
Okay, let's thank Hiranya again. The second speaker of today is Xuelei Chen, and he's going to tell us about 21 centimeters cosmology.
Can you hear me? Oh, okay. So good morning, everyone, and also I thank the organizers for inviting me to speak here. The talk, my talk is about 21 centimeter cosmology, which is unlike the what the previous speaker have mentioned. You already have a lot of measurements. With the 21 centimeter experiment, we are still striving for it, but there is a great potential. So what is 21 centimeter? For those people who, for example, working on particle physics and not familiar with the astronomy aspect, this is the transition in the ground state of the neutral hydrogen atom. So the neutral hydrogen atom have in its ground state actually is split into two hyperfine states. Because they have a different, the spin of the nucleon and the electron could be either parallel or anti-parallel. So this transition produces photons with wavelengths of 21 centimeter or frequency of 1420 megahertz. So this is the ground. So this shows the energy state of the neutral hydrogen atoms. These are the two transition, the two ground state splitting. Of course, there are also these more familiar Barmore transitions to n equal to. Maybe I should read 2 here. It should be 1. To generating the lemma alpha and lemma beta photons. And during this transition, of course, for example, you could transit from ground state to the first excited state and backwards to a different hyperfine splitting. And so these transitions also modify the state here. So why is 21 centimeter interesting? the universe, as we know, we can probe its structure using a number of different tracers. So the neutral hydrogen actually provides also a tracer. So during the early universe, of course, we have the Big Bang. And during the Big Bang, the hydrogen ionized, so we won't have this kind of transition. But after the Big Bang, the universe enters the so-called dark age, where you don't have any stars. But at this point, already the neutral hydrogens are there, and in principle can be probed by the 21 centimeter. And later on, of course, the first generation of stars form, and we can see this neutral hydrogen generating or generating 21 centimeter signals. And then, of course, these stars begin to shine and generate photons which ionize the gas around them. So in the end, we have the reionization of the universe, where again, most of the gas in the galactic medium are ionized. So, but still, the neutral hydrogen would be present in the galaxies, so we can still probe them. So because of this picture, we generally, most of the co-moving volume of the universe can be probed by 21 centimeter. So for example, here we show that the CMB was generated at this last scattering surface. And when the CMB just the last scatter, of course, afterwards, the universe enters the dark age. For a while, the 21 centimeter signal will not be present. I will explain later. But then for most of the co-moving volumes, we can use various ways to probe it. And also the hydrogen is primordial, so that it's observable even during this dark age or cosmic dawn period in principle. And also in the universe, there's a lot of hydrogen making up 76% of the baryons. And finally, you can see this, for example, on the same scale, if you show the optical galaxy and the 21 centimeter line revealing the distribution of the neutral hydrogen, they look different. So they may be different, they produce different kind of tracers. So that is good because that gives you an opportunity to compare the results and also to do the cross correlations to reduce the cosmic variance. So here are different modes of observation for the 21 centimeter. You can do the tomography, where you measure both in the angular direction and also measure different frequency or wavelengths, which corresponding to different redshifts, so that you map out the three-dimensional structure of the universe. You can do the 21 centimeter forest, which, like the Lambda alpha forest, you look at the high redshift bright source, point source. This needs high angular resolution. I will not particularly talk about this in this talk, but it also gives you a lot of, in principle, gives you a lot of information. And finally, there is also the simplest kind of observable, which is the global spectrum. You measure the whole sky, and as this circles shows that even though you have all the sky, you do not have angular directions, but you get the different frequency corresponding to different redshifts. So that also tells you how the neutral hydrogen evolves during the history of the universe. Now, the 21 centimeter signal is determined by the both the density and the ionization state of the hydrogen, as well as the spin temperature. So the spin temperature shows how the different two levels, atomic levels, are occupied. So this is defined the way the T star is a constant. So basically, it shows the spin temperature determines the relative ratio of these two states. But this spin temperature is a temperature. So actually, it's described by a thermal system with a very small heat capacity. So the atomic motion and the Lambda alpha photon scattering, as well as the CMB, all affects the spin temperature. So the spin temperature is basically a weighted average of these three systems' temperature, and depends on how strongly it coupled to the three. weighted temperature, the spin temperature also differs. So the atomic motion means that the usual kinetic temperature we are talking about for the gas. Now, during this gas movement, they can atomic have collisions, and during this collision, the spin could flip. So this try to couple the spin. Now, if the gas is very thin, then the collision is infrequent. In this case, maybe it will couple to the cosmic microwave background, which are the photons of the same energy, which have photons of the same energy. But finally, if there's a lot of Lambda alpha photons which transit between the ground state and the excited state, that also affect the spin temperature, moving it towards the color temperature of the Lambda alpha photons. But these Lambda alpha photons actually, because they repeatedly scatter with the different atoms, so they actually have the same temperature as the gas kinetic temperature. So this is a complicated system, but in the end, it's kind of driving the spin temperature as a weighted average between the two. So these are the different ways that the spin temperature can be modulated. There could be the density fluctuation, there could be the neutral fraction, and of course, also the spin temperature, which I have mentioned. And of course, the gas temperature itself also evolves during the history of the universe. So all of this information is combined into the spin temperature and gives the result. So you can use it to probe a lot of different things. Now, beginning with the dark age. So during the dark age, initially the gas have the same temperature as the CMB. So when we look into the sky, we will not be able to see the difference. But then the gas will drop below the CMB temperature, and one could, in principle, use this to measure the gas fluctuation. Although in reality, this is very difficult. But in principle, this gives you a lot of different Fourier modes to measure. So actually, it contains a lot of more information than the CMB. That would be in the future, because currently this would be very hard to do. But when the first stars begin to form, these first stars will generate Lambda alpha photons. And as I mentioned before, the spin temperature of the gas is below the initially below the temperature of the CMB. So that they form a halo, which you can see a significant 21 centimeter absorption signature. So that's one of the signatures of the first stars. But of course, the stars also heat up the gas. So later on, this absorption transits into emission, and eventually, of course, the gas is ionized, so you won't see the signature anymore. And then on the larger scales, this is for individual stars, but on the larger scales, there are also this reionization process where initially you form a number of these stars which ionize the gas around them to form this is white patches. And then as the number of them grow and the size of them grow, they begin to overlap with each other, eventually making the whole universe ionized. So this is the so-called reionization, and is currently one of the central focus of 21 centimeter study. So to model these things, you could do radiative transfer simulations, and also you need to model the galaxy formation. Now you can make some simple computation, because the radiative transfer and the semi-analytical model are both very expensive. So you can also make very simple models based on the following idea. So the ionized region size will be determined by the number of ionizing photons. Of course, also depends on the recombination, but basically, it's the number of ionizing photons and the number of ionization recombination. And these can be computed by assuming that a certain number of baryons collapse to form star-forming halos, and they will generate a fixed number of photons. So you can use this to calculate. This is so-called bubble model by Folanito, Zadarriaga, and Hörnquist. And so now you can also further improve this. For example, our group recently proposed the island model, where after these bubbles begin to percolate, the remaining neutral regions also get ionizing background photons. And that would be proportional to surface area. So you can model the number of the neutral regions. So here I show a movie of this simulation. Can you? Yeah, so here shows that as the regions initially begin to form ionizing photons, they will kind of ionize most of them, but then there will be patches where with low density remaining what we call the neutral islands. So you can also model these. So once with these models, of course, you can come up with observables such as the 21 centimeter power spectrum, which, as I show here, it depends on the baryon density fluctuation, the fluctuation in ionization fraction, and the fluctuation in also the Lyman alpha photon distribution and the temperature, and so on. And this is a redshift distortion. So you can come up with the predictions on the 21 centimeter power spectrum. And this evolves, this shows different redshifts. So basically, initially you have a small power spectrum, but then during the e-power ionization, the power spectrum is enhanced, but eventually it's come down back again. Now there are some limitations on the power spectrum, so people have also been developing other observables like peak counts and the bias spectrum and so on. And also, one can use the cross correlation with other observables. For example, the 21 centimeter Lyman alpha emitter. There are many such studies. I apologize for not being able to present all of them. Just selected two. For example, you can count the 21 centimeter Lyman alpha emitter. So you can see at some scales they are anti-correlated because the Lyman alpha emitter is more present in the high density regions, which are ionized first. So initially you will see, of course, this different. Depends also on the different ionization fraction or neutral fraction. And also you see initially on these scales, small scales, it's anti-correlated, but on larger scales, it's approach constant. And also you can do cross correlation with the X-ray background and many other backgrounds. In this figure, I show that during the redshift, actually this cross correlation evolves. So you at some redshift you have anti-correlation, and at some redshift you have a positive cross correlation. But in this case, for example, the anti-correlation is the strongest, so that the integrated effect would be determined by the strongest place. So that gives you a probe. So by exploring this kind of cross correlations, you can study the reionization. And you can also study the post-reionization. So, for example, this is the shows that after the reionization of the gas in the intergalactic medium are ionized, but the neutral hydrogen recedes in the galaxy because there you have a higher density and a higher recombination rate, so that remains neutral. And this shows the alpha survey mass function shows that for the you can see down to very small masses, 10 to the 6 solar masses, you still have a neutral hydrogen. To smaller, this is a H1 mass. For smaller mass, H1 mass, maybe it's going to be ionized by the UV background. There are still some differences between the different measurements. Maybe the different environments also affects the H1 mass. And then you can come up with models of how this gas exists within the halos, and compute also the autocorrelation and the cross correlation of these. These are the observables, and then you can use it as the tracer of the large-scale structure and doing things like a baryon acoustic oscillation, the primordial non-Gaussianity, and inflation features. This just shows for our experiment, Tianlai, the predicted, the forecasted BAO measurement precision and the dark energy measurement, and also the possible constraints on inflation generated the resonance features. Finally, you can also look for the evolution of the global spin temperature. So during the redshift, the universe history, as the redshift evolves, the 21 centimeters are different because the global spin temperature changes. So as I said, initially the CMB and the gas have the same temperature, so the spin temperature would be equal to the CMB temperature. So initially you don't see any signal. But then during the middle dark age, for example, redshift 160 to 80 or maybe 60, you will have some absorption because here the gas drops below the CMB temperature, and the spin temperature approaches the gas temperature because here the gas is dense enough for the collisional coupling. And then as the first galaxies form, it generates a lot of photons and produces strong absorption trough. And afterwards, as gas also heat up, so you begin to see some emission. And finally, when the reionization ends, you approach to the zero 21 centimeter global signal. So this kind of thing can be measured in principle by looking at the average temperature of the sky. Now, that's the models. So what about the experiments? So let me say something about the experiment here. There are experiments which use existing telescopes, and there are also experiments which build dedicated experiment. So traditionally you can do the H1 galaxy survey. You try to observe each galaxy just as in the optical surveys. But in the radio, this is not very efficient because in the radio wavelength is long. So you kind of to achieve the high resolution to resolve individual galaxies, you need a very large telescope or a very large array of telescopes. But then its sensitivity would be low for these very large arrays because they can't be very sparse. So instead, people come up with the intensity mapping idea. Instead, you not look at the individual galaxies, but measure their intensity. And because you want to measure these BAO's wiggles, so the size of these are probably optimal for about an array size of 100 meter, in the sense that with this, you can already detect the peaks. And of course, the larger array, you will detect even better. These also have large field of view, and so it's good for detecting the fast radio bursts. The difficulty is that there's a strong foreground, which is maybe 10 to the 5 times stronger than the 21 centimeter signal. So you can, in principle, you can remove these foregrounds because they are smooth, and you can subtract the smooth foreground and recover the signal. Now, for the interferometer array, what you actually do is to measure the cross correlation between the two, each pair of the receivers. And because the wave's direction is different, so they are delayed for different time. And if you measure the what we call the visibility, you get this result. And it looks like that for each pair, you get each baseline, you get one of the Fourier mode of the sky. Now the problem is that well, let's see. So you have these different experiments. For the epoch reionization experiments, there have been LOFAR in Holland and Europe, and paper in China. There was 21 CMA. Paper is in is American experiment in the South Africa, and the Australians have the MWA, and now also the paper people have moved on to what we call the HERA experiment, to also in South Africa. So these are the paper in the background. And eventually, the HERA will be made up with about 600 antennas. And also, there is the SKA law in Australia, which are aimed at building many, maybe 256 stations. Each station have many antennas, a total of about 130,000 antennas to observe the sky. This two approaches, this tries to use the identical baselines to make a very precise measurement on the power spectrum. This is having a more randomized baseline distribution for imaging. And then for the mid-redshift, which probe the dark energy, there are also many experiments. CHIME in Canada and Tianlai, which I lead, and are the two which have been built. There are some experiments not dedicated to this dark energy, but also serve as the pathfinder of the SKA. That include the Meerkat and the SCAP. There are existing telescopes such as GBT and PARCS. And finally, there are also the HYRAX in South Africa being planned, and the BINGO in Brazil also being planned, and FAST in China, the 500-meter dish, which have finished the construction and is starting to doing observation. So these are the sensitivity estimates for the cylinder arrays, such as the CHIME and the Tianlai, which basically measures a strip of the sky and try to measure the power spectrum to get the BAOs. For some of the arrays, for example, the SKA, it has not completely, well, it's designed for many different purposes. So for these BAO measurements, we actually need baselines at the 100-meter distance or so. For these SKAs, their distance are further apart, so they are not entirely suitable for these, but they can be use the single dish mode to observe the sky, serving as, for example, 200 dishes to observe the sky, but also using the interferometer mode to observe, but look at the along the line of sight direction to measure these BAO wiggles. So this is a comparison of all these different BAO experiments. And by the way, okay, so you are welcome to join the SK Cosmology Working Group, which discuss what's the cosmology to do with the SKA. I'm sorry for running out of time, but let me just say a little bit about my own experiment. The Tianlai experiment is try to, it's a pathfinder with 3 cylinders and 16 dishes. The cylinders have 15-meter wide and 40-meter long with 96 dual polarization receiver units. And we observe initially at 700 to 800 megahertz, but it can be adjusted. So if it's successful, it will be expanded to larger scale. So we looked through China and to find the best site with very few radio interferences. This is the site. The station house. The array is actually about 7 kilometers away from the station house. So these are the the cylinder array and the dish array. So these are the cylinder and the dish. And it has been operating since September 2016. This is the first light data showing the over 3 days. The observations seems to be relatively stable. And one can do analysis and get the these are the initial image we made of the sky corresponding many of the previously known bright sources observed, but there are still some false images which we are processing. Now, these kind of things are very hard because there are mode mixing foregrounds, so even though in principle you can subtract them out with very smooth response, in reality your response is not smooth and not well known. You have to measure them from the calibration process. So in reality, the signal is can be quite complicated. So this is a PCA analysis of GBT observation. And you can see when you do the PCA analysis, actually the foreground modes, except the first one, which is very smooth, most of modes are very complicated because this cross-coupling or leakage of these effects. So for example, in this GBT analysis, we detected cross-coupling between the cross-correlation between the optical and 21 centimeter signal, but it's still far from the one order magnitude above the autocorrelation signal. So in other experiments, people also found right now the 21 centimeter has not yet succeeded. So you get this kind of wedge structure. This shows the K perpendicular and the K parallel. So you cannot measure these very small K parallel modes because of the smooth foreground. But then in principle, you can detect this these modes with large K parallel, which will not be contaminated by the foreground. Let me also mention that recently there are this breakthrough in the global spectrum. In the global spectrum, you try to measure the sky, and these are previous limits from the H experiments. They initially look for the detecting the change, the reionization epoch. But now they also begin to look for the absorptions at the cosmic dawn. And there are a number of such experiments. Besides the H, there are also the Sci-Hi prism in Mexico and South Africa, and the Big Horn in Australia, and the Saras 2 in India, and LIDA, which is in US. And this is the H experiment. They did painful work to try to make very precise calibration of the system so that they can know their response precisely. And they detected this strong absorption trough, which is actually a little bit
Excuse me,
yes.
If you could please conclude.
Yes.
It's very interesting, but...
Yes, sorry.
Thank you.
Yeah. So anyway, so this actually is stronger than the maximum signal predicted by the theory. So there are many different interpretations. One possibility is that there may be astrophysical foreground, but they are not looks not like the signal detected. But on the other hand, you have so much stronger foreground, so a slight difference could result in this false detection. Here is some of our work which we show that actually if you consider inhomogeneity, the case is even worse. People have thought about other interpretations, for example, early extra-radio background or the strong dark matter interaction, which can serve as a heat sink to cool the gas and generate this very strong signal. So these are actually the model can, for example, can explain it if there is a very strong dark matter and baryon interaction. But in order to not violate the CMB effect, you also have to have it velocity dependent. But then there are many constraints on this when you're considering the physics. I'm sorry I ran out of time, so I will not go into the details here.
So please, let's conclude,
yes,
please.
Yes, so I'm concluding, yes. So finally, I was saying that, let me mention that we are also conducting experiment which will use the satellite circling the moon to make very low frequency measurements, which avoid this ionosphere effect. Because I ran out of time, I will not continue. And but if you are interested, please come to talk with me.
Thank you very much. Thank you. So, in the interest of time, only if you have a very urgent question, and if you can keep it quickly, just one question. If you please keep it brief.
Short question. To check the edge absorption features by future experiment, is it possible to reduce the thermal noise on the Earth? Thermal noise.
Thermal noise,
yeah.
you mean?
I'm worried about thermal noise at around less than 100 megahertz.
You're saying you can reduce the thermal noise?
Yeah, in future experiments.
I think right now the thermal noise is already dominated by the sky. So you of course with longer integration time and more copies of the same antenna, you can also reduce it in some sense. Yes,
yeah, it's possible. Okay. Thank you.
Okay, let's thank Xuelei again. Thank you. And the last speaker of the session is Fernando Quevedo. He's going to tell us about cosmological implications of string theory moduli.
Okay, good. Okay, so let me start thanking Kiwon and all the organizers of this conference, which has been very, very interesting and very well organized. And it's a pleasure to be here, and also to see that the level of science and the different institutions here are so high, which is good to see for the future of science in Korea. It looks very good. But so I will talk about the cosmology of string moduli, and in principle I will talk about 3 papers. The 2 ones I was planning to talk about, which was something that came out last year, oscillons from string moduli, and a more recent one in the June, moduli stars. But recently I got involved with these issues about quintessence and ensemble. And there will be a paper appearing today. I was checking, and it hasn't appeared yet, but the number will appear today. So I will talk about this because this is the subject of conversation on many of the informal talks here. So Marco, you don't mind if you stop me around 10 minutes before, so I can have time to take. Yeah. Okay. So let me start. So this I will go one by one. So a short review, because we have a different audience here, mixed audience. So in general, string theory predicts, one of the things that we can actually say for sure is that string tends to believe in extra dimensions, 6 or 7 extra dimensions. And it has been a major problem over many, many years, is to fix the size of extra dimensions. In the times of Kaluza and Klein, when they proposed the 1 extra dimensions, to explain why this extra dimension is smaller compared to our dimensions, has always been a challenge. And it's only this century that it has been really approached with the fluxes and moduli to fix the moduli, the modular, the size and the shape of these extra dimensions. And there are several scenarios that came out starting from 2000, 2002. And then that has allowed us to start exploring concrete consequences from from string theory, because before that, you don't fix the size of the extra dimensions. You don't know how to do the calculations, because at the end of the day, all these moduli will be flat directions in 4 dimensions. They will create many problems for field forces and so on, and it will be inconsistent with any experiment. And so from both sides, it was important to fix, and it's only at this time that people started working. At that time, precisely, the idea of having the acceleration of the universe came out, and then we had some of the solutions had the Sitter space as a solution, so that means the positive cosmological constant, and that has been very much debated recently, so I will discuss it later on. So, moduli, in general, are scalar fields in 4 dimensions, and so they are good candidates for inflatons. That's one of the good things. They have usually gravitational strength couplings, so in that sense, that would be very difficult to detect in experiments here. The mass of the moduli is usually the gravitino mass, and the gravitino mass measures how much supersymmetry has been broken, and is not well known how big it can be. It can be from TeV above. And each modulus actually is a complex field. It has a real and imaginary part. So the real part is kind of a saxion, and the imaginary part an axion. So it's always they come together. We have to consider them together. And the number of moduli, there are many, and usually that depends on how complicated this manifold is, and it can be between the other hundreds or thousands of them. So that's rough number. So to stabilize the moduli, people have been using there are 3 types of moduli. For this discussion, I will concentrate on one particular string theory, which is called type 2b. And there are many reasons to discuss type 2b and not the other ones, and I will mention them later. Is the one that we can do calculations. It's not that it's better than the other ones, but it's the one that we can do the calculations. And at the end, we have 3 types of moduli: the dilaton, which is the modulus of that measures the string coupling, is existing in 10 dimensions already. The sizes of the 4 cycles inside the 6-dimensional manifold, and the sizes of the 3 cycles, and they have labels I and A because they are the ones that can run into the hundreds. And the effective field theory is a standard supergravity theory, which has this scalar potential. And then the progress that was made is that you have a superpotential, which is non-trivial. The superpotential is generated by fluxes around the different cycles, and that is a function only of the U fields and the S fields. The T fields are special somehow because they have a Peccei-Quinn symmetry, a shift symmetry that people have been talking about during the conference. And so being the superpotential holomorphic, it cannot depend on the real part nor imaginary part of T. So at tree level, on all orders and perturbation theory, the superpotential depends on U and S, but not on T. And then once you plug it into the standard supergravity potential, you get a potential that happens to be positive definite, because also the T fields satisfy one particular property, which is called the no scale, which is the K inverse KK equals to 3, so this 3 is cancelled. And then the potential is positive definite, so the minimum is when each of these quantities are 0, and that fixes the fields S and U, but not T. And since they are 0, the potential is 0, and that's at tree level. Then there will be quantum corrections. So I will go slightly in detail here because this will play a role at the end of my talk. The quantum corrections are important because since the potential is 0 at tree level, so the leading order quantum correction will be the ones that dominant for fixing this fields T. And since the basic quantities are the Carrier potential and the superpotential, you can estimate the variation of the scalar potential is the order of W0 squared delta K plus W0 times delta W. So this is the variation of the superpotential, the variation of the Carrier potential. And so this brings you to 3 different options. One is that the standard one, the tree level is bigger than the corrections. The corrections for the superpotential are always non-perturbative, so they are very small. And the corrections to delta K are perturbative, so they're also bigger than delta W, just usually. So in this case, only this term dominates. and that will go, that delta K goes like 1 over the volume, so that'll give you runaway behavior. And that's the standard problem that people call the Dine-Sauer problem that came out in the 1980s. They're saying it will be very difficult to stabilize the moduli because they tend to run away. But there are two other options that have been explored in the last 15 years or so. One is that the KKLT is the famous KLT scenario in which you use the fact that this flux's superpotential is, there's so many options that you can tune essentially this W0 in a way that W0 can be very, very small by tuning the different fluxes, because there are hundreds of them, and you can make it at the same order as the delta W, the non-perturbative one. And in that case, since that W0 is very small, you can, this term dominates over this one, you can neglect that one, and then, but there will be a delta W square corrections, and the delta W square compete with this one, because W0 is the same order delta W, and that give you a minimum, and that's what the standard KKLT scenario is. And but then there's the other solution is make these two terms compete with each other, and that's the large volume scenario. In that sense that the corrections to delta W is non-perturbative, the corrections to the Keter potential are perturbative. So typically they go like 1 over the volume, whereas the delta W goes like exponential of one of the moduli. If there is only one modulus, tau and volume are essentially the same, and then it will be impossible for these two terms to compete. But the good property of string theory is that there are hundreds of this, so you can compete the volume, overall volume with one of the small moduli. And so this term competes with that one, so these two terms compete with each other. And since that will give you that this delta K is for delta W, so 1 over the volume is equals to e to the minus a tau, so the volume is exponentially large. So that's the reason to have large volume, that's the name. So essentially these are the two scenarios that came out and that people have been exploring over the past years. So, as I told you, now we have stabilized the moduli, and then there will be ways to lift and how some of the minima are de Sitter and some of the minima are anti-de Sitter. And so then you can play with that and get inflation. I will go quickly with this because this is not the main point of my talk. You have to keep in track, in mind that you have to keep the hierarchies to work. The Planck scale has to be bigger than the string scale, and bigger than the Kaluza-Klein, and bigger than inflation. That puts a strong constraints on what kind of inflation you can get. And that's one of the main reasons that it's hard to get very high scale inflation. And and then you have 3 epochs: pre-inflation, inflation, and post-inflation. Pre-inflation, we have usually nothing to say, unfortunately. Inflation, then we can start using this effective field theory approach to get inflation. And then what I will concentrate mostly today is in post-inflation. The interesting thing is that usually people say inflation is good because it erases everything that came out before, but also it's bad because it erases everything that came out before, because then you may not see any signatures of what happened before inflation. However, the moduli, again, are the things that survive after inflation because they are light. They are light fields, so even after inflation happens, they survive, and they have, as I say, mass of the order of the supersymmetry breaking scale, so they can play a role after inflation. Just to give you a taste of the moduli, one is the overall volume, the size. The other ones we call blow-up moduli, which are like a Swiss cheese, are small cycles that when they get bigger, the volume gets smaller, which is. And then there are other ones like a fiber model, like when you could locally, it is like a product space. And each of them have different structure, and then the potentials can be different, and they can all be candidates for inflation. And then there are concrete inflationary models that give you NS and R in the potentially observable regime, which is here. Okay, post-inflation. The most important thing that happens post-inflation is that these fields, whatever happens to inflation, these fields are the moduli, being inflatons or not, they can, at the end of inflation, whoever the inflaton is, these fields, they are stuck in some place which is not its minimum, and then will start oscillating. And when it oscillates, it behaves like matter and then dominate the energy density of the universe. And it's only after they finish oscillating and decay that's the real reheating. So reheating is not after inflation, but it's after this field decay. And it can be much later than the inflation part. That puts a strong constraint on the masses of this field, which is heavier than 30 TeV or so. That used to be called the cosmological moduli problem. But since the fact that we haven't discovered supersymmetry, 30 TeV is not a big deal. So now we call that moduli domination period. So it's a period where moduli dominate the energy density of the universe, depending on the mass. Okay. So then let me just talk about the oscillons. That's the first paper, oscillons from string moduli. So oscillons, in principle, they are localized, long-lived, nonlinear excitations of the scalar fields that people have been studied over the years. So the generalities is that you just have a field here. At some point, you start oscillating, and you have to solve the corresponding equation for the field in the Freeman-Rosen working background, and then the perturbations. And the perturbations have this term here that can become negative. So in that sense, it will become, say, tachyonic, and they can give rise to growth of inhomogeneities. So you can have unstable solutions. There are several effects. The parametric resonance, when one of the modes has coincide with the resonance, the natural resonance of the corresponding field. The tachyonic preheating, that means that above here there is an inflection point. Above here there is like a tachyonic behavior because this quantity is negative, and that can give rise to inhomogeneities. Yes. And then tachyonic oscillations. The field can start oscillating, and once it passes, every time it passes the inflection point, it will behave tachyonic, and then that will create inhomogeneities. So that's what these oscillons at the eventually will be produced. So there are necessary conditions for oscillon productions. Quantum fluctuations of the field grow as it oscillates around the minimum. The growth of fluctuation is sufficiently strong for nonlinear interactions to become important. And the potential, this is the important part, the potential is shallower than quadratic. So you have the quadratic piece minus something. This is typical for axions, for instance. You have this minus sign. And so then you can have an attractive force. And that's what when you have, that can be the effect that compensates for the pressure and stabilize the object. And so in order to explore that, we have to do lattice simulations to solve the equations, and also including the metric perturbations. And for that, we take the KKLT part, the case. This is the potential. You have to go to the canonical normalized field, and then you see the inflection point here, which is the critical quantity, and then see if you have enough oscillations and that they can grow, the perturbations can grow or not. So for different values of the flux superpotential, remember it has to be very small for the solutions to exist. For 10 to the minus 12, for 10 to the minus 5, the inhomogeneities grow, but not enough. In this case, not enough to produce oscillons. But in this case, when their W0 is smaller enough, that you can produce oscillons. And but the main effect here is parametric resonance. You can see the field oscillating around the inflection point, around the minimum, and so, but you don't have enough. While it is oscillating here, the oscillation the perturbation don't grow enough. So it's only after here. So then you can see the snapshots. You can see a movie. You can follow our paper, but you can see some snapshots of how these inhomogeneities are created, and you can see how they are coming up. Also, they don't come out spherical as usual, as expected. So in that sense, you can see them to be a source for gravitational waves. And you can see the gravitational waves spectrum. So for different here for different times, you can see that they have a very well defined spectrum for these oscillons. But unfortunately, the frequencies are very high with the corresponding amplitude. We can reduce the frequencies, however, at the expenses of reducing also the amplitude. So it's something we have to think. Okay. For the blow-up modes, the one that I was showing to you with the Swiss cheese shape, actually you do get tachyonic oscillations enough to make to increase. This is a much more dramatic behavior, the same kind of shape, but actually the slope is such that it's much more dramatic. So you can actually produce this growth of perturbations, and here you can have this tachyonic oscillations giving you rise to oscillons. And in this case, you can see the real how this field, these configurations are being created, and the amplitudes again, the gravitational waves produced are bigger amplitudes. So I'm a little bit behind with time because this is my second, so let me just go fast. Now moduli stars. So having studied this configuration of oscillons, they have been stabilized by the structure of the interactions. However, gravity is there, and gravity can also play a role to stabilize these objects. And so for that, we remind the fact that there are fermion stars. We have gravity compensating the fermion pressure, and you get an object which has a maximum mass proportional to the m Planck's cube or m square of the mass of the fermion. For mass of 1 GeV, you get a solar mass, and that's the standard neutron star. And for boson stars, there's a huge literature starting in the 60s, ideas of Wheeler and many others later on. And that actually is, you can argue from that you can have the Schwarzschild radius competing with the Heisenberg principle, the uncertainty of the radius are proportional to 1 over m. So you get objects with a maximal mass, not m Planck cube or m square, but m Planck square over m. And so for a given mass, this is much, a given mass of the field, this is a much lighter object. And people had argued that can be interactions, and most of the literature in boson stars are saying that you have big interactions that can reduce the mass to a similar level of the fermion stars. However, in string theory, we don't find them. We only find things of this type. And so the bosonic compiled objects, you can have cuboles and oscillons, which are repulsive pressure against attractive interaction. You don't need gravity. And the cuboles are like non-topological solitons. But then you have gravity as repulsive source pressure, like we have boson stars, mini boson stars with the masses that I told you, then oscillatons for which the axion stars are there. So it's a source of jargons. I think David Marsh mentioned mini clusters also in his talk. So are there stringy boson or fermion stars? And they're the candidates, the modula, the modulini, the gravitini. These are the fermion stars, and this could be candidates for boson stars. And for fermion stars, the standard possibility for the gravitino and the modulus. Of course, if they are stable and they can be, or quasi-stable and can be dark matter, that can be object that survives now, but if they decay, still there are objects that play some role in the history of the universe. And for that, you can compute the corresponding masses. The volume cannot be arbitrary, so it has this range of values. So then you can have different masses and sizes of these objects. You can have this thing, something of the size of a nucleus with as heavy as the Mount Everest or so. And then the volume model can also be a star. Then we can solve the equations with the Einstein-Klein-Gordon equations on the field with an oscillating part with you can see how the profile is such that is more or less localized here, and this is the evolution of the gravitational interactions. And you can find solutions for both KKLT and LVS. Then you can look for cuboles in string theory, and you can find them in the open strings. It's all work by Kusenko for the MSM directly applies to string theory, so you can have open string modes giving you rise to cuboles. But the closed string sector, you can also get them in several ways. Either when you have moduli and actions, the action being much lighter is one of the general predictions of the string. Of the large volume scenario is that the corresponding action partner of the volume has a mass which is extremely small because the volume is exponentially large. So it's e to the minus something that is exponentially large. So it's doubly exponentially small, so this is essentially 0. And that's a good candidate for an ultralight action. So usually people talk about ultralight actions, and then in this scenario, they come out very natural because the corresponding field is already stabilized and is heavier, but the action is essentially massless. It can be one of these exponentially large. Unfortunately, I'm running out of time, so I'll skip this. Just to give you a general picture, we can have the states, the corresponding field, the corresponding star. Usually there's a duality of 1 over the volume going to the volume, and everything depending on the volume. You give the volume and you get the whole spectrum of this object that you can get. And the spectrum of masses that you can get from different sizes and mass to relatively small to extremely big. It's just given by this action that I told you. Okay, de Sitter versus quintessence. So this is the source of debate. So I will spend 3 minutes on that, or 5 minutes. So there have always been challenges about getting de Sitter. You have how to define an asymmetries in the Sitter space. People would say, well, is it just a resonance or is it a metastable case? There are classical no-go theories about getting de Sitter in string theory. That's not a big issue because we know that atoms are unstable classically, so in that sense that's not a problem. However, but the argument has been used recently, which I think is good to take into account, is that there are no de Sitter solutions on string theory under full calculation and control. So the cases I told you, KKLT, LVS, and so on, they're very interesting. There has a lot of considerations, but they're not on the full calculation and control, and that's a fair statement. However, jumping to that and say that they're totally not under control is not fair neither. So it's not under full calculation and control, but they're so there have been a couple of studies in the recent years to criticize some of the steps of this KKLT and large volume scenarios. If the flux is under control, only if you have supersymmetry you have full control, otherwise you don't. The tuning of W0 is not just achieved. People say that there are good arguments to see it, but it's not seen in the concrete models because it's very complicated. What about higher order corrections that can change the large volume limit? Usually, since the volume is very large, the approximations get better and better, but we cannot just say 100% sure that everything is under full control. And there was some criticism for anti-branes. They create some singularities. Also, they're introduced by hand, and they're not supersymmetric. However, this has been debated and discussed, and in the last few years, people say that they have agreed that there's not an issue there, and so on. So then there's the Swampland conjectures. The Swampland idea, I think, is very good. The idea is that effective field theories, not every single effective field theory can be derived from a theory of gravity. And I think Matthew Rees would talk about them, that the weak gravity conjecture and the distance conjecture, they have been very much extracting people information that not everything that you can see at low energies is actually achievable in quantum gravity, and that's a good way to distinguish what things you can actually get from string theory or quantum gravity. But then there's this recent one. The recent one is very strong, based on these arguments that the calculations are not under full control to get de Sitter. So, Obiet et al. Conjecture that you will never get de Sitter. Essentially, that there is a bound, that the gradient of the potential is, or the potential is greater than a positive constant, the further one. And so essentially it will imply quintessence, because then the fields have to roll, and not de Sitter, but also it will be very difficult to get inflation, because this is that will be one of the slow roll conditions will be broken. So this has been the source of a lot of debate in the last few weeks. So let me just say that still the Sitter have many achievements. It's remarkable that people have been obtaining that. So we don't have understanding of string theory. We don't have a full non-perturbative understanding of string theory, and yet we have been able to extract all this information that I told you before, and under very stringy things from branes, orientifals, anti-branes, perturbative and non-perturbative effects, and so on. Then this 2B theory, the Bodley space is well understood, and people have control and so on. And then there is a control of the hierarchies. All the scales are under control. The Kaluza-Klein scale is more than the string scale and so on. So you can separate different scales. Okay. 1 minute, sorry. Now there are challenges for this new conjecture. There are two challenges that have been already raised in the literature we have explored. One is that if a gradient, if the gradient has to be bigger than some quantity, what about the Higgs potential itself? The Higgs potential, you have a maximum at h equal to 0. So that's the gradient is 0. So then the direction of quintessence would not compete with this height of the TeV of the Higgs. So you have to find ways to make that quintessence consistent with the Higgs, and that's challenging, which we have approached. Also, the potential, if it goes to 0 from above, you have to come out down, and then even supersymmetric. If you forbid de Sitter, you can also forbid some ADS supersymmetric, and so in both cases this can be addressed if you just modify the conjecture to still allow saddle points for bit minima, but saddle points. But there's, I would say, no real concrete reason why to impose this. And so then you ask the question, and this is my last point, sorry, is can you get quintessence from string theory? And the challenges are the same as getting the sitter, plus more, plus getting this slow roll. You have to get all models stabilized, plus one of them rolling. So in that sense, whatever is difficult to get in the sitter, it makes even more difficult to get quintessence. And yet you have to address this. And then people have studied quintessence candidates using this moduli that I told you, or inflatons. Actually, our main organizer, Kibun, has been one of the leaders in using this action as quintessence. And this is the last point I will emphasize today, and this I will finish. As I told you, we have many moduli. Each modulus has an action, and the potential for the actions, if you have these ultralight ones, at the end you can integrate everybody out except for the actions, and then the potential will look like this. Notice that I put different constants here and there. People usually put here 1 minus cosine, because assume that the minimum is at 0. That you cannot get in string theory. It's totally unnatural. So in this ways, these two things are different. And then you have to compute, the source of this term is completely different from the source of this term. So they don't have to be. So you can play with the relative values of them. And the condition to get quintessence is the epsilon is smaller than 1. And so usually this is used to imply that FL is bigger than M Planck. But here it's not necessarily, because it depends on the ratios of these two lambdas. And so then we have different possibilities of getting quintessence depending on how the field is. You have very close to the hilltop. If the constant term is much bigger than the running, or if the field is oscillating, that will give you a very interesting equation of state which is fluctuating. So, conclusions. So there are concrete models of inflation for string theory, which is good. But inflation is only one component of the cosmology. Post-inflation is very important. I explored several things. Things for dark matter, dark energy, dark radiation, actually. These light actions are typical cases, for example, for dark radiations. And then there's a rich spectrum of compact objects, oscillons, gravitini, modulini, modular action, and stars that can have some signature, in particular gravitational wave signatures. I like to say that eventually, in the long future, we can hear the shape of the extra dimensions by just seeing this gravitational wave spectrum for each modulus will give you some different patterns. And the sitter versus quintessence, there are many achievements, which is good. There are many challenges, which is also good. There are many open questions, which makes the field much more exciting. And I would like to end with this comment of Mark Twain, so the report of my death was an exaggeration.
Thank you.
Thank you.
Yes, please.
Of course, the dark matter and action, those kind of things may be contained in the string theory. But my question is a bit general. The string theory, or maybe moduli, has something to say about cosmological constant problem, or is it outside of the string theory?
No. That's a very good. That's precisely the point of this. So you have all these many solutions. So you have all these fluxes. So actually, if I would say, this is the only concrete solution of the cosmological constant, even though people don't like it, which is precisely that. You have all these hundreds or thousands of fields, fluxes of fields. There can be all this combination of integers that will give you a huge amount of minima. And how many minima is many? Say, as people say, 10 to the hundreds or so, or more, 10 to the thousands. And then that addresses, this is the anthropic argument for addressing the cosmological constant. So this is the only concrete way to do it. So this tuning that I was telling you about, for instance, getting lambda here in the last slides about the action potential, is precisely the tuning of the cosmological constant. And the rest we are talking about, there are just small fluctuations around that. So that's why this issue is very debated, because it is the basis of that is addressing the cosmological constant problem, and that's how it's important to have it under as much control as possible, and it's not yet under full control. So we cannot claim it's under full control because we haven't found cases where you have the hundreds of models, like giving you this W0 very small, for instance, or the tuning to be possible, and also how to populate the vacuum, how to go the landscape, how to go from one minimum to another one is not yet under full control.
Okay, next question.
Okay, you mentioned this action-like quintessence, but on the other hand, because action is a compact field, you necessarily has the digital maximum. So that might be in conflict with this digital swampland conjecture.
Absolutely.
What is your opinion
Very
on
good.
that?
Exactly. So thank you for asking. It's the three. Let me see yes, each of this, for instance, here. You have to be very close to the maximum, and this conjecture in principle is forbidding the maximum. But you say, well, let's now use the modified conjecture, where they accept saddle points and not minima. So then this could be consistent with both. It's very bad. It's very tuned, but these two you cannot. These two, they both have to have a minimum. As you said, it's a compact, you have to have a minimum. And in both cases, the minimum is at positive cosmological constant. You can have quintessence also on top of that. But in these cases, you have a minimum, which is the sitter. So you can have quintessence and the sitter together. But
Sorry, let's keep it brief because we are already.
So basically, you assume you take this modified version of the digital swampland conjecture, which allows the unstable maximum.
Yes, they agree with that. Yes.
So one final question over there.
So you show that the relation between the size and the mass of compact objects, right? Then I'm wondering if it can be ultra compact. So I mean, it can be the Schwarzschild radius.
Yes.
Or comparable. Okay.
Yes.
Okay.
Exactly. Yes.
Thank you
Exactly.
very much.
Yeah. So what we're giving is a maximum mass, and yes.
Okay, let's thank Fernando and all the speakers of this morning. And I think we will resume in 20 minutes.
All right, so we are going to start the second session of the morning session of the third day. The first speaker is Risa Wechsler, going to talk about mapping the dark universe with galaxy surveys. Yeah.
And in addition to talking about how we actually do that with telescopes, I'll talk about the role that simulating the universe has in how we extract cosmological constraints from those maps. So just to put this talk in the context of what Hiranya told us about this morning, we really are in the situation where we have a standard cosmological model that is almost established independently by the cosmic microwave background measurements and gives us this very precise, essentially 6-parameter lambda CDM model. And even though I listed, I think, 8 parameters here, one of them says that the universe is flat, and then one of them says that the dark energy equation of state so far is consistent with the cosmological constant. So in that context, we want to test whether this model works over the span of the whole universe. So that 6-parameter model makes very precise predictions, just starting from the measurements of the cosmic microwave background for both the expansion history of the universe and how structure grows. So we really would like to understand, does that model also describe the late time universe at high precision? So in a little bit more detail, is the early universe and the late time universe, are they described by the same parameters? Do measurements of the expansion history and the growth of structure agree with each other, which provides then a test of general relativity on the largest scales? And is it really true at higher precision that the dark energy equation of state is consistent with being constant over space and time? So the main lesson that I want to give you today is that there is significant additional information about the late time universe, both about dark energy, which I'll focus on, but also about dark matter, inflation, and neutrinos. So this is, I think, in Hiranya's phrasing, radical conservatism, that I'm going to talk about how can we measure the parameters better, can we break the model, and, you know, if we're all lucky, discover some new physics. So sort of the ongoing, and I think next actually 15 years of cosmological surveys that we have mapped out is going to enable us to answer these questions and really test this paradigm at much, much higher precision. And one of the things that I want to leave you with is that, in my view, the ultimate power of how much science we can get out of these surveys is also going to depend on how well we can make predictions. And that includes how well we can make predictions for structure on the full range of scales, and also how well we can understand galaxy formation, how well we can understand galaxies and their connection to the matter distribution, and even how they impact the matter distribution. So I'm going to be talking about both imaging and spectroscopic surveys. And just to set the landscape of that, there's a large number of such surveys. I won't talk about all of them. I'll talk really only about the ones in yellow with a primary focus on DES. So with 2D, with imaging surveys, we basically get a 2D map plus a fuzzy third dimension. And, but imaging surveys give us weak lensing, they give us cluster abundance, they give us galaxy clustering, and they often also give us the time domain, including supernovae and strong lensing. With a spectroscopic survey, you get way fewer galaxies, but you get a much more precise map in 3D. And the really nice thing about that is it allows you to very cleanly separate the growth of structure from the expansion history of the universe through these two probes, baryon acoustic oscillations and redshift space distortions. And so if we can measure those two things, the growth of structure and the expansion history, we get a very nice test of GR. And these surveys also have significant additional information, including information about the mass of the neutrinos and inflation. And that's going to be especially true if we can keep up, if the modeling can keep up with the data. Okay, so I'm going to just mention these three cosmic surveys that I am personally working on. The Dark Energy Survey, which is really ongoing right now. We're actually just finishing data taking later this year. But our first major cosmology results were actually released about a year ago and published this week. So that's an imaging survey of about 300 million galaxies. That was a new camera built for the Blanco telescope in Chile. It's about an eighth of the sky. On the twin of this telescope in Arizona, there's a new spectrograph being built, actually 10 new spectrographs being built for this instrument. And this instrument, the DESI instrument, will have 5,000 fibers and an 8 square degree field of view. So it'll be able to take a large number of redshifts at a given time. And we plan to do a spectroscopic survey of 35 million galaxies, actually starting next year. So it's super exciting. This is going to be an order of magnitude more spectra than we currently have. And that's over about a third of the sky. And then Hiranya already mentioned the Large Synoptic Survey Telescope, essentially the largest ground-based project in optical astronomy. A new camera being built down the hall from me at SLAC. It's going on a new telescope that's being built right now, 8.4 meter telescope. And this will survey the sky for 10 years. And we'll be able to do lensing with something like 10 billion galaxies over half the sky. Very exciting. So our DES cosmology results were actually just published this week. When these results first came out, there was a lot of press, and this is my favorite story that came out, that there's a terrifying dark universe within our universe. They got the concept a little wrong, but this did the Dark Energy Survey Year 1 results did really confirm the presence of dark matter. We made this beautiful map of dark matter over 3% of the sky. And that's about 1/3 of our final survey map and about 40% of our final depth. So, what I'm going to tell you about today is just based on this. It's 20% of our total data. We're working hard now on essentially 3 times as much data, and we'll finish observing later this year. Okay, so these are the 2 maps that we made with this Year 1 cosmology survey. And just for context, I've put our survey validation data here. This was just a small piece of sky that we did from the early data. So this is a map of the galaxies, and this is a map of the matter distribution. And this map of the matter distribution we get using weak gravitational lensing, using essentially the small distortions of about 20 million galaxies in this patch of sky. And with these 2 maps, the core cosmology constraint that we pushed on was something that we called the 3 times 2-point analysis, and that's because we're just looking at 3 different 2-point statistics. So we're looking at the clustering of galaxies, the autocorrelation function of galaxies. We're looking at the clustering of the shapes of galaxies, so the cosmic shear, and then we're looking at the cross correlation between them, the galaxy-galaxy lensing. And so by putting these 3 pieces together, you can actually simultaneously measure both cosmological parameters and bias and break some of the degeneracies between them. So there were about 14 papers that came out in this initial release, and then Ashley is going to tell you about some of the other results just in the next talk. So I'm not going to talk about the baryon acoustic oscillations, which came out of this. So this key paper actually had lots and lots of little pieces that went into it because we had to make the measurements very carefully. A really important piece of this is understanding the photometric redshifts, because we only have a 5-band imaging survey. And one of the things that I want to highlight here is that realistic simulations of the survey were really core to the entire program. And so the papers that I've highlighted in yellow are papers that used these realistic mock surveys of DES as some part of understanding their analysis. And so within the collaboration, we actually had 2 independent pipelines, one done by my group and one done by the group in Barcelona. And so I just want to highlight a little bit about what are the different ways that we use simulations in cosmological analyses. Because I think they're increasingly important. So the first thing is that we need simulations to make accurate predictions. We're in the highly nonlinear regime, and we can really only do this with large simulations. So, whoops. So that includes really basic things like the mass function and bias of dark matter halos. But as we start to think about a survey like DES, it also includes many complex statistics. So cross-correlation of galaxies with the CMB, galaxies with clusters or underdensities, cross-correlation between imaging and spectroscopic surveys. So all of these things, we need to be able to make really robust predictions for these things as a function of cosmological model and our model for how galaxies populate the dark matter distribution. The next thing is that we really need to use simulated surveys to do systematics estimation and marginalization, and that includes both theoretical systematics like galaxy bias and intrinsic alignments, and also data systematics, things like photometric redshifts, star-galaxy separation. Many of those things you want to do as much as you can on the data, but it really helps if you can test that methodology on the most realistic simulation possible. And then the last thing is really validating your whole pipeline. And one of the very new things that we did with DES is really validate our entire cosmology pipeline end to end. And so I'm going to tell you just a little bit about that. So first I want to just say a little bit about how we actually do those simulations. So again, we're trying to simulate the entire DES survey. This is quite hard. We want to do multi-probe cosmology. We want to do these analyses in parallel. So we need a really lightweight strategy. Ideally, we'd love to be able to simulate the entire universe with all of the physics that we know and love and resolve the details of every galaxy, but we're very far from that. So we really want to use the lightest weight strategy we can, and we want to get to really realistic observables. So that includes things like how the galaxies are clustered and the impact of gravitational lensing, lots of other basic properties. So I just want to mention this review article, which actually was also published this week in annual reviews, which actually goes through the different approaches that the community is taking to understanding the problem of how galaxies are connected to the dark matter distribution. And there's a whole range of approaches, sort of from more computationally expensive and more physics included here, to a bit cheaper and more parametric on the right-hand side. And in my view, all of these are very useful, and they're complementary to each other. And there's essentially synergies between how we can learn, between the different models. But for this work, as I said, we wanted a very lightweight strategy. And so we do sort of a small high-resolution box, and we use that to tune essentially the lowest resolution pure n-body simulations that we can get away with. And that allows us then to do many realizations of those simulations and test out our galaxy scheme, test out different cosmological models, and actually make tens of realizations of a large survey like DES. So these are just a few images from these simulated surveys. So in a paper coming out soon, we'll have 30 realizations of the DES Y1 footprint. And this starts with n-body simulations, but it goes to galaxy catalogs, shear, and all of the detailed galaxy catalogs that we actually use for the analysis, including photometric redshifts. And one of the things we use those simulations for is to really test our pipelines. So, we want to know really specific individual pipelines. So is my photo-Z code accurate enough? Is my red sample selection, what does it do to my cosmology analysis? And we also want to do full cosmology analyses. And so I'm just going to focus on this one due to time. And so this is an example of, I mentioned this 3 times 2 point measurement. And what we do here is we basically do that measurement in parallel on the data and the simulations. And in this case, we did it on 18 realizations of the DES year 1 sky. This is looking at the shear in data and simulations. This is looking at the galaxy clustering in data and simulations. So we then actually run our full cosmology pipeline. So this is still simulated data. And one of the things we first were able to show is that in these simulated universes, again, 18 realizations of the footprint, we showed that the cosmic shear and the combination of clustering and galaxy-galaxy lensing were consistent with each other and both consistent with the true value in the simulations. And one of the nice things is that we actually had these 2 independent groups. The other group was also, so the analysis was run on both. This one, you'll see the error bars are much larger because they were not able to do 18 realizations. You do actually need, of that order, 20-ish kind of realizations of a survey like DES to show that you're accurate enough within the error bars of the measurement. So, so that's an important thing to know for looking forward to the future. Okay, so let's move on to the real data. I don't have a lot of time to get into the gory details of the analysis, so I'll just give you some highlights. So this, again, is the 3 times 2 point analysis. Here, we're showing the comparison between the shear alone. So this is just the lensing measurement, which is about a factor of 2 increase in constraining power compared to previous measurements. And then the galaxy clustering and gamma theta, which then combine to give us these contours. So this, analysis used 4 cosmology parameters, 10 parameters that were sort of nuisance parameters characterizing the clustering, various bias parameters, 10 that characterize the lensing. And we also minimize the impact of various systematics by making a scale cut and basically not using the small scales of our data. So there actually is substantially more information in the data if we're able to do that modeling better in the future. So as we already heard this morning, DES, in this plot we show the comparison between DES and Planck. And in this case we are marginalizing over neutrino mass. And really for the first time these have comparable sizes of error bars. Okay, so this is a constraint on the matter density. This is a constraint on S8, or the normalization of the power spectrum on an 8 megaparsec scale. And so there is a difference in central values, but there is no clear evidence for inconsistency between these measurements. It certainly motivates us to get smaller error bars in the near future. And as we heard, yeah, so this is just 20% of the data. We'll have 3 times as much data in the data that we're analyzing now, and that will be the full footprint. An interesting thing is that these data do actually agree with the other large lensing survey, the KIDS survey. So in this case, the error bars are larger because we're only looking at the lensing, not the 3 times 2 point. And this is saying that those lensing surveys are currently really agreeing with each other, and even though they're a little bit offset here. So the bottom line of this result, since they are consistent, we can combine them to get very strong parameter constraints, and we are still finding that these data plus Planck plus BAO are consistent with the simplest model for dark energy. So there is a lot more to come. One of the things that will be coming very soon is an analysis from the galaxy clusters in the same data. So this is a little more than 6,000 clusters over the same area, going from redshift 0.2 to 0.65. There's a lot of great things about this analysis. We have a very well understood cluster finder, which has excellent photo-Zs. We have a really detailed model that accounts for all of the systematics, including projection effects. We use the weak lensing data to do the mass calibration, and X-ray data to inform both our systematics modeling for centering and projection and our scatter. And so for the first time, we have a 5% calibration of the mass richness relation. So that's really exciting. So this mass calibration paper came out earlier this year. So the plots you're looking at here are just the projected mass profiles around of the dark matter around galaxy clusters in 3 redshift bins, and then in bins of cluster richness, so more massive systems over here. And the error budget is really dominated by 3 things. 1 is the photometric redshifts, 2 is the projection effects, and 3 is the cluster triaxiality. But we think we understand these things quite well and have detailed models for these. So this is what the constraint is going to look like. This is a blinded analysis, so I have no idea myself what the real answer is yet. What we've done is just shifted the axis to be right on top of our 3 times 2-point analysis, so that does not mean they agree. It's just that this is to show you the size of the error contours. So in this version of the plot, there's actually no prior on the scatter in the mass richness relation. And already we're getting a really nice tight constraint on omega matter and a pretty tight constraint on sigma 8. If we actually add a quite reasonable prior on that scatter from X-ray measurements, those contours come down even a little bit more. So they're a tiny bit larger than 3 times 2-point, but really quite comparable. And I think this is really exciting because this analysis has almost entirely different systematics than the 3 times 2-point. Obviously, it's the same galaxies, but it's not even the same photometric redshifts that come in to dominating the analysis. So there really is very different systematics that are dominating this. So we should know the answer about this comparison quite soon. Okay, so I want to mention that these 3 times 2-point papers were published in PhysRevD this week. And there will be a data release of all of the data products from those papers later this week, I think in 2 days or something. And there's new analyses coming imminently from clusters and also combining the 3 times 2-point with CMB. I think we've learned a lot from this early analysis that's going to push us towards the future, not only of DES, but also of LSST. And we're really sort of learning how we combine various probes. So I think there's a lot of richness in the data that's going to allow us to take this much farther than you might have thought with just simplistic assumptions of having the probes being separate. There's also still a lot of power in smaller scales if the modeling can keep up. So I'm going to just spend a few more minutes talking about what we need in terms of accurate predictions for the next stage. And I'm going to talk about a particular effort that I've been working on with collaborators called Emulus. And this is an effort essentially to build emulators for various kinds of statistics based on suites of dark matter simulations. So the basic idea is that we're beyond the point where we can just sort of write down an analytic function for what the mass function or the clustering of the objects we're looking at looks like. I think the best way that we're going to do this going forward is really just simulating these things directly and building emulators that give you predictions for the specific statistics as a function of cosmological model and galaxy model. So we're using suites of high-resolution n-body simulations and interpolating the statistics. So we do in this case, we did about 40 simulations that span a 60 parameter space, and we do an extra set of 35 simulations to test how accurate they are. And I just want to say something about my philosophy for this field going forward, because I think this whole approach is about to explode. And people are taking different approaches, and I actually think that's great. I think we need people to do this independently, and we'll learn a lot from each other. But my personal philosophy is to really think carefully about the problem you want and design the simulations, for that problem or that set of problems to be as lightweight as you can and as close to the data as possible. And by that I mean, don't just do an emulator for for just the mass function or the bias, but go all the way to galaxy clustering. So just very briefly on this, these are some results from our mass function emulator. We do need about % level precision. So in this paper, we were able to get from error bars that look like this to error bars that look like this much smaller error. And that is actually good enough to get us through the first year of LSST. It won't be good enough for the next decade, but it's good enough for the next 5 years. Okay, in my last few minutes, I just want to say a little bit about the DESI survey, the next big spectroscopic survey that's coming up. So DESI, as I mentioned, is building a new instrument that will take 5,000 spectra at a time. We will get roughly 35 million galaxies and quasars and another 10 million or so stars. And our philosophy here is really to try to probe as much volume as we possibly can. So we're looking for the easiest galaxies that one can get redshifts for over the broadest possible volume. So we'll be observing about 1/3 of the sky. We are almost done taking the imaging data for this survey. That's been done with a combination of telescopes, DECAM, the same as Dark Energy Survey, the Bach telescope, and the Mayall. And all of that data is being released publicly on a 6-month schedule. So I encourage you to dig into it. So in the nearby universe, we'll actually get about 10 million bright galaxies, down to about R of 19.5. Then we'll get LRGs, emission line galaxies, and quasars. And the main idea of DESI is really, it's designed as a baryon acoustic oscillation survey, and Ashley is going to talk about that in the next talk, so I'm not going to emphasize that here. But I just want to emphasize these beautiful kind of predictions for our measurements. So these are sort of current measurements for the expansion history from BAO, and this is what we expect to have by the end of DESI. And the really wonderful thing that you get from DESI is that you can separately measure this expansion history from baryon acoustic oscillations and the growth rate from redshift space distortions. And we'll be getting both of these things to much better than 1% over most of this history. So with that, we will get very tight constraints on dark energy, but it also has information about inflation and about the mass of the neutrino. So DESI plus CMB, we expect to get an error bar of about 0.017 eV in the sum of the neutrino masses. So that is, should be enough to distinguish between the normal and inverted hierarchy for neutrino masses. So I just I'll say a few words, one more word about an emulator as it relates to the kind of science we'll be able to do with DESI. So I mentioned that we'll be doing redshift space distortions, right? So that's the idea that when you look in galaxy clustering, it's got some anisotropy along the line of sight from the motions of the galaxies. Now, the thing that we promised to do with DESI is only focused on fairly large-scale redshift space distortions, still pretty much in the linear or mildly nonlinear regime. But I think we can do substantially better if we can push to smaller scales. And so in this paper, we took a first step in that direction. And what we showed is that a nonlinear analysis is about a factor of 2 better than a large-scale analysis. And about half that constraint comes from the quadrupole. And this is the error bar as a function of scale. So you can see that the error bar gets smaller as you go to smaller and smaller scales. So this is going to require accurate predictions, which is not trivial, but I think that this is totally achievable. And so what this does is it can break the degeneracy between the growth rate and the normalization of the power spectrum. So just to give you a feel of how beautiful these data will be, this is what we currently know about the density of galaxies at redshift 0.3, and this is what DESI will be able to do at that same redshift. So you can see that there's a lot to be done when you can map the universe in that way. So just to emphasize that we are going to start taking data in just a little over a year, and my hope is that in the first year, we actually will be able to do about 2,000 square degrees that overlaps with lensing surveys. And so that gives a really rich data set to test lots of very interesting things. Okay, so I will end there, and I will just leave you with this idea that we really are just at the beginning of this new era of cosmic surveys. DES is already doing very well at for the first time, sort of testing the predictions of the CMB in the late-time universe. And we expect to have quite a bit more soon, including the cluster cosmology. DESI is going to provide really exciting constraints on growth and expansion. And we're going to have to think about a lot about various kinds of systematics. And one of those things that we're going to have to think about is how do we make predictions in the most lightweight way possible and a way that's really relevant to our data analyses. But I think that's very possible. I think we'll need this sort of combination of realistic survey realizations and sort of emulators that go directly to the various statistics that we're trying to do. And in my dream world, we're going to be able to do this on relatively small scales to get all of the information that's available. So thanks so much.
So we have time for 1 or 2 quick questions. Yeah, Risa.
Yeah, just a small naive question. So you talked about richness, which I understand is an optical mass proxy, right?
That's right.
And then X-ray as well. So how do they agree between the optical mass proxy and the X-ray mass proxy? I mean, the scatter between the two. I mean, is it large or is it?
It's actually not very large. So there's 2 separate questions. Does the calibration of the mass richness relation agree? And I think that currently, within the error bars, it is in pretty good agreement. That actually was in my slides. I think in the interest of time, I won't bring it up, but I'm happy to show you that plot. In this particular analysis, what we're doing is actually just using the X-rays as a constraint on the optical scatter. And we find that it's actually not very big. I think it's the constraint that we're using is 0.25 dex plus or minus 0.1. So it's actually much smaller than you might have thought.
Okay. With your permission, one more quick question.
I think we have very limited, so
okay,
we can
fine.
continue.
No,
Any more question? Yeah, go ahead.
Hi. So you mentioned lightweight method, a lot emphasized on that. I wonder if you, I noticed you used Gaussian processes for the emulator. I wonder if you have any thoughts or considered the more recent developments, such as deep learning or generative adversarial networks.
Yeah, we actually have been working on that. In our published work, we only used Gaussian processes. We're working on an emulator now that sort of simultaneously does clustering, so where the parameters are cosmology, HOD, and assembly bias. And we actually are finding that, that neural nets are more effective than Gaussian processes for that emulator. So it's something we're playing around with. And I think I don't think there's one right solution. But yeah, it's definitely interesting. Thanks.
Cool, thank you.
Okay, so let's thank the speaker. So the next talk is by Ashley Ross. He's going to talk about measuring dark energy properties with the galaxy surveys.
Is that right? Should have paid attention to the other people more. All right. Hello. Thank you very much. It's great to be here. Yeah, so I'm going to give a bit of an overview about our current constraints on what we know about dark energy, with an emphasis on what we learn about it from galaxy surveys, and an emphasis on what we learn from these kinds of surveys that I'm a member of and work in. Okay. So I think one thing that even for an audience like this that it's important to remind people of is that dark energy is pretty crazy. The universe is accelerating. We didn't expect that 20 years ago now. This iconic cover's almost 20 years old now. When we found it, of course. And sure, a cosmological constant fits all the data, but a cosmological constant, while being nice mathematically, is pretty weird. It doesn't make sense from a particle physics standpoint as a vacuum energy. And I've heard of some pretty disturbing consequences from quantum mechanics and entropy arguments that it means like an end of history. We'd really like to probe this further and figure out if really the data is consistent with a cosmological constant, and if so, well, what solves these other problems? So that's the essential question is, can we find a departure from this lambda CDM model that fits all the data we know pretty well so far? Basically, we want to know is, can we complicate this pie chart? Can we remove the words dark from this pie chart? There's been a lot of talk about doing that on the cold dark matter side. We would like to do that on the dark energy side. Maybe it will be a cosmological constant, or maybe it'll be something different. So there's different approaches. One is to look at the equation of state for dark energy and see if we can get a departure from -1. That's the equation of state for lambda. And we use this common parameterization, which I think we stare at this a lot. But really, to remind you, so we have W naught, which is the equation of state today, and WA, which is really how much the equation of state varies over the history of the universe. So that's an important thing to keep in mind when we look at the allowed values. Another thing we like to look for are any deviations from GR in the hope that perhaps a modification to gravity will naturally explain a cosmological constant. And then there's a third approach, which is, well, can we find tensions in the data that exists? And if we drill down on those tensions, will they point the way in any way forward? And then we do this work with combinations of distance and structure growth measurements. So our current understanding is nicely summarized by this plot from the Planck collaboration recently. And this is W naught WA, and it highlights a lot of things very nicely, I think. So one is that we need much more than just the CMB in order to understand dark energy. The CMB is amazing, but it's only one redshift, so it doesn't give us the dynamics that we need, the measurements as a function of time, in order to probe dark energy. Another thing that it really highlights is that a lot of the information that allows us to close these contours, to actually learn information about the equation of state of dark energy, comes from galaxy surveys. Basically everything on here is from a galaxy survey except for the supernova component. And then I think the final thing that this nicely highlights is, WA can have a value of -1 is allowed there. So that's a pretty big change over the history of the universe in the equation of state for dark energy that's allowed. And so in what follows, I'm going to focus on how we learn this information from the galaxy surveys that allows us to pin down the nature of dark energy. And again, we do this with distance measurements as a function of redshift. That's one way that we measure the expansion history. We have the standard candle. That's the supernova type measurement. And then we can also do this with standard rulers. If we know the true size of something and we measure its angular size, then we know how far away it is. And that's, we use the baryon acoustic oscillation feature in the distribution of galaxies to measure distances to those galaxies. And we can also use structure growth. That's a little bit of a less direct probe of dark energy, in that what we're really probing with structure growth is the matter density as a function of time. That is, of course, related to what the dark energy density is. And we're essentially just measuring the amplitude of matter clustering as a function of time when we do that. And it's very obvious how much structure has formed when we look at the very early universe to today in these simulations. But I think one thing that's interesting to point out is if we looked at the amplitude of the power spectrum between just redshift 1 and today, that changes by a factor of about 2.5 over that amount of time. So there really is a great amount of expected evolution in the structure formation, and that's why we can use it to test dark energy. So there are many observables we can use to test dark energy. This is only a few of them. We, of course, use the CMB measurements sort of as really, especially when combined with BAO as a linchpin. It gives us everything, but again, it's only one redshift. We have the direct H0 measurements. Hiranya talked about those earlier. That's really building off from Earth measuring distances to local objects, and we would really like to compare what we get from other means to those measurements and see them agree. As we saw, there's a bit of a tension right now. And we have the most famous supernova, type 1a. That's how we first discovered dark energy. But then from galaxy surveys, we have the BAO distance measurements. That's what I'll focus on for the talk. I'll also talk a little bit about redshift space distortion measurements that we get from the same surveys. And then Risa nicely covered what we get from weak lensing and clusters. So just a word on what we mean by a galaxy survey and what I will mean for the surveys I'll be talking about. So we put a camera on a telescope and we observe in many filter bands so that we can actually make color images on the sky. So there's a very high signal to noise version from the Hubble Space Telescope, but that's the essential idea. And we can look at this image and we can identify many galaxies by eye, and we can even see that some of these are much redder than other galaxies, and those galaxies that are much redder are probably further away. They have higher redshifts. We can do a rough photometric redshift by eye on those galaxies. So we can roughly split up the galaxies as a function of redshift when we do that, and we can analyze what we see in 2 dimensions with some tomography, because we can do that rough splitting in redshift. But then we can also go ahead and say, okay, well, if I could gain access to another dimension more precisely, measure the redshift of these galaxies. I want to measure redshifts in redshift range 0.2 to 0.4. Roughly, I think galaxies with this color will have that redshift. We then target those galaxies for spectroscopy, and we get a redshift that allows us to precisely we get a precise redshift that allows us to make a 3-dimensional map from those galaxies. But of course, we can't do that for every single galaxy in this image because we don't have the resources for that. And so probably still the premier example of this is for actually doing the redshift survey is the Baryon Oscillation Spectroscopic Survey, BOSS. It's complete now. It was part of the Sloan Digital Sky Survey 3. First, we obtained imaging using the Sloan telescope at Apache Point, New Mexico, in those 5 bands that I just showed you. Then the camera was sent to the Smithsonian, and then we put the BOSS spectrograph on the telescope, and we started getting spectra for those galaxies that we targeted, so we could make our 3D map. And we got redshifts for 1.2 million galaxies over about 1/4 of the sky, between redshifts 0.2 and 0.75. And so in order to do this, the targets were chosen, and a tile, we call them, for one observation, was sent so that we could drill aluminum plates with holes so that we could plug fibers into those plates and then load this cartridge onto the back of the telescope and observe the light that goes down each of these fibers and get a redshift for each of those. And so these were all plugged by hand, 1,000 fibers at a time, and then loaded onto the back of the telescope. And then so what these are showing here are the completeness of our spectroscopic observations, basically the fraction that we observed compared to the fraction that we would have liked to observe. And so you see a pattern that looks like there's overlapping circles on there, right? And that's just because of the observational strategy where we plug these plates and put them on the back of the telescope. So that gave us this map over core of the sky. And so this is these same 2 footprints now, but now showing the entire sky So we have BOSS in orange, and then the footprints of the other data that I'll be talking about as well. For eBOSS, we're using the same telescope, same spectrograph. Instead of the 9300 square degrees, we'll get 6100 square degrees, and we're going to higher redshift than we had in BOSS. We'll get about 1 million more redshifts. Then for dark energy survey, we don't have galaxy spectra. We rely on the photometric redshifts, but we can still measure the transverse BAO scale. And so I put a little squiggle, 10 million here for the number we'll use, because we're using photometric redshifts. We actually do some selection. We decide, well, what redshifts actually can improve our measurement. So there's a little squiggle there. And then there's also about 160,000 sightlines used for Lyman alpha forest 3D clustering measurements that can also be used for redshift greater than 2.2 BAO from BOSS and eBOSS. And so what we do with these observations is we make a map, we make a three-dimensional map, and so this is actually from very early BOSS data. You can see the rich structure of the cosmic web just from our BOSS galaxies. That's putting them, so we have their angular coordinates and then just their redshift coordinate. So here's a smaller slice. We make these maps and then we analyze the 3D clustering. And the primary science driver for BOSS and eBOSS is to find the baryon acoustic oscillation. And this is basically, we're looking for the same signature of acoustic peaks that you see in CMB, but now in the distribution of galaxies. After the time of the CMB, the standing wave that gives you the acoustic peak stalls, and it just expands with the expansion of the universe and stays the same co-moving distance, so that we see an excess of galaxies at that sound horizon scale. And that gives us a standard ruler that very nicely corresponds to what we observe in the CMB, and therefore the combination of the BAO measurements plus what we get for the CMB ends up being a very powerful cosmological probe. And what we actually measure is the BAO. We see galaxy pairs along the line of sight and transverse to the line of sight. So then we actually get a distance measurement along the line of sight and transverse to the line of sight. Along the line of sight, that gives us the expansion rate at the redshift of the galaxies, h of z. And transverse to the line of sight, we get this co-moving angular diameter distance measurement. And that's illustrated here. This is from actual BOSS data. This isn't a model. You can see there are little noise signatures in here. It's processed the non-BAO component of the best fit model, subtracted out, and higher order multiples along the line of sight have also been filtered out. But this is the actual data that we observe for BOSS. So extremely high signal to noise measurements of the BAO feature. Some with early on in the stages of these surveys, we typically don't get such high signal to noise. So we'll typically combine the information into this dV quantity that gives us this combined distance measurement. So this is an approximately current BAO distance ladder, now splitting things into these co-moving angular diameter distance measures and h, and for surveys that only measure dV, the dV. So at high redshift, as Hiranya pointed out earlier, there is a bit of a tension. So these lines here, that's the prediction for the best fit lambda CDM model from Planck. I think this was the 2015 version. There's a bit of a tension there, but everything else agrees very well with just that prediction from Planck. And what I'll show the rest of the way will be this compressed version. It's easier to show everything there together and compare the precision. But an interesting thing happens to Lyman alpha when I show this compressed version. Here, so now the h of the piece and the dm piece gets averaged basically, and it ends up being consistent with Planck when you average it in that way. So in the plot that was similar to this that Hiranya showed, it was just the DM piece that was on that plot. So this is actually our current BAO distance ladder, including recent measurements from dark energy survey and recent measurements from EBOS. And we can use these measurements and we can forget about the CMB for a second and just say, well, we believe BAO is a standard ruler, and we can discover dark energy again at very high significance, greater than 6.5 significance, just with BAO. This is in an open lambda CDM model. And so that's nice, that's consistent, another independent probe of dark energy. But the power really comes when we can combine it with a CMB. This is now combining with Planck 2015 from a couple of years ago. And so this is, if we just have a constant equation of state, as pointed out previously, we actually have pretty tight constraints on that. It has to be very close to -1. And we learned that after combining basically Planck, supernova, and BAO together. So this is in a model allowing open curvature. I guess on behalf of BAO people, I apologize if anybody was really rooting for negative curvature. Because of the combination with BAO and the CMB, it gives you a very tight constraint on the curvature and puts us back into perhaps the more boring region. But as I pointed out earlier, when we open things up and allow time evolution, there's a great degree of time evolution allowed in the equation of state for dark energy. And one thing you should really take home from these plots is it's really the combination of BAO and supernova that give us any hope of really shrinking these contours to the degree we need to really learn something. And another thing to take away, so there's this plus FS here. That's when including the information from what we call the full shape of the galaxy clustering. That also gives us significant improvements over just the BAO. And I'll talk about that a little bit more in a minute. But first, another reason why we really love BAO, other than it just being this powerful dark energy probe, is it's a very robust dark energy probe. Observational systematic effects don't affect the BAO measurement, and that's what this plot is supposed to illustrate. So this black line here, that's our clustering measurement for EBOS quasars that we recently put out about a year ago. The gray dashed line is if we don't correct for some selection effects that we know about. Basically, the number of quasars we observe changes depending on how good our data was. But we can correct for that. But whether or not we correct for that, we get actually exactly the same BAO measurement to within 0.1 sigma. And it's a 13 sigma effect on the clustering. So there's an extreme effect on the actual clustering, but no effect on the BAO measurement. And we knew that BAO was pretty robust previously from BOSS measurements, but the actual selection effect that we had in those previous measurements, that was more like 4 sigma. Now it's 13 sigma, it's still no different. And we also believe that theoretical systematics are small. Issues due to galaxy formation, galaxy bias, we believe are less than 0.5% and most likely much less than 0.5%. There are some issues, so you should see a poster by Jamor Givens back there that could give us this sort of level, and those will be important for the future for DESI. So the full shape information that I mentioned previously, that essentially comes from redshift space distortions. Redshift space distortions are essentially a structure growth probe, and that's because on large scales, galaxies will want to flow towards larger overdensities, and that'll give those galaxies a peculiar velocity, and that will basically squash how they look in redshift space. When we take a redshift and say that that's a distance, the distance to the galaxy moving this way will look further, and the distance to the galaxy moving this way will look closer. And we see that in the clustering of the galaxies. This is the clustering amplitude. Now the raw one, nothing filtered, and you see the BAO ring again. And what you see is that the clustering amplitude, these are not circles. Instead, it's more like an oval. It's squashed, And that's due to the fact that galaxies are flowing on to larger overdensities. And that flow, that's just the structure growth. We'll have more flow into overdensities if there's more matter, less if there's less. And essentially, the degree of that squashing is the amplitude of the velocity field, the amplitude of the large-scale velocity field. And one thing you can do other than just test dark energy properties when you have that information is also look for any sort of departure from GR. So this is one thing we did with the BOSS data. This is basically the amplitude of the velocity field. Given the lambda CDM model, that gives you a prediction for what the value of F should be given the omega matter at that redshift. And we can look for departures and find that there's no significant departure from what we'd expect for GR. And we want much more precise probes of this in the future. So I agree with what Hiranya said earlier about H0 being the most significant tension that we have. And another plot from the Planck 2018 paper that I think is very interesting and highlights some very interesting aspects of this H0 tension as it deals with BAO measurements is this really isn't just a Planck versus local H0 measurements tension. It's also any probe of the sound horizon plus any way to constrain omega matter versus local H0 measurements. And the degree of inconsistency gets worse and worse depending, as you add in more data closer and closer to the actual Planck data. But so it's worth just going through here. So in green, that's BAO. So our BAO distance measurements, which alone don't say anything about H0 because there's a perfect degeneracy between H0 and the actual sound horizon scale. But if we add in supernova, which give you omega matter, and Big Bang nucleosynthesis constraints, which give you the baryon density, then you do get an H0 probe, and it prefers a lower H0 there in green than the local ones. You wouldn't say it's huge tension, but it's a slight tension. And then here in red, this is very interesting. This is now if we only take Planck as a standard ruler. That's the theta MC. So ignore everything else and add it to the BAO and these other measures, and you get a very significant tension now with local H0. And then, of course, we know if we combine all Planck, it's a significant tension. But actually, this is pretty similar. So one thing that this says, to me at least, is say you're 100% convinced in the local H0 data. If you can think of something that changes the sound horizon scale without somehow messing with the rest of the primary CMB, then that could shift your H0 value. Now, it's very hard to think of anything like that. I don't believe that's probably what's going on, but that's one potential that you could think of. For instance, we do know of effects that change the sound horizon scale, like the number of effective relativistic species, but those sorts of effects also change the rest of the primary CMB and get ruled out. So you have to think of something pretty weird, but something along those lines. So in the near future, EBOS and DES will get much more precise results. These are data that we have now, data that I'm involved in analyzing right now. And so these aren't just pure forecasts based on survey design. These are forecasts based on what I've seen. So within the next year or so, our constraints will look something like this. Where these dots are has stayed exactly the same, so those will probably move around a little bit. But coming actually quite soon is DESI. As Risa mentioned, we'll get more than 30 million galaxies, and we're going to be on Sky in 2019. That's really soon. For some people who are working on it, that is frighteningly soon. We got to get a lot of stuff together. But it's getting built. It's coming together. It's going to be awesome. And we're going to measure 5,000 galaxy spectra at a time. And that's how we're going to get these 30 million galaxies, an order of magnitude increase in the number of galaxy redshifts that we have. And so this actually requires pretty major changes in the technology that we use. 5,000 is too many to plug by hand. That would just be, carpal tunnel disasters. And another issue is that when we do this, these fibers, they get loaded into a cartridge that gets put on the back of the telescope, and a cartridge gets changed out every time you want to observe something new. There's a lot of time wasted there. So, because of both reasons, we have 5,000 robotic positioners for DESI that will basically allow each one of these positioners has 2 motors and allows it to go any location within its patrol radius. This is what the full focal plane looks like. There's 10 pedals here because, as Risa mentioned, there's 10 spectrographs. And all these little robotic positioners, they have to move around and not collide with each other. And we have to know that if we tell them to move a certain place in X, Y, that'll correspond exactly to a certain place on the sky. So there's a lot of work that we are frantically doing in order to make that all work. But the positioners work. We have them all. And so with DESI, this is what the BAO constraints will look like when it's done. So you can compare that to what we will have very soon to what we will have with DESI, and you can see, oh man, we are going to be filling in this distance redshift relationship with BAO measurements in the future to just an amazing degree. And this will give us really nice constraints on dark energy. So here's what we have now. So here's a forecast, which is just combining Planck and different configurations of DESI. It also includes BOSS BAO. So basically the gray here should be the same size as the blue here. And the size of the axis here, that's the size of the black box. So we're really zooming in here. So if by chance, WA is at -1 and we can do redshift space distortions out to k of 0.2, that's what this implies, then we would detect that at many sigma. So that's pretty exciting. So my conclusions, I think probably everybody knew coming in this, there's no strong deviations we have from lambda CDM right now, but I really want to emphasize there's a huge amount of time variation allowed in the dark energy equation of state. It can change by 1, and that's just at 1 sigma over the lifetime of the universe. So we really need more data in order to learn more, and thankfully much more data is coming with DESI, and I didn't even mention Euclid or WFIRST or all the other great surveys that are coming out in the future, or how much better these constraints will all be once we add in weak lensing and clusters on top of it all.
Thanks, Ashley, for a very interesting talk. So questions? Yeah.
Comparison of the DESI and other instrument figure. So I think this one next one.
This one?
Yes. So
yeah?
could you explain a bit more about the meaning of these right-hand figures? I mean,
sorry. So this is so here. Here most of the points on here are actual distance measurements we've made with BAO, and we've divided out the prediction for what these distance measurements would have been in the best fit Planck lambda CDM model as of 2015. And a few of these are forecasts based on data that we have right now. And then on the right, this is the forecast for DESI. So all the points are at 1. Obviously, these will scatter around, or maybe go off of the prediction, and we'll find evidence that W does not equal minus 1 at all redshifts. Is that?
Any more question? So actually, I want to ask one thing myself. So you showed that interesting plot from the Planck, that the H0 problem is not only from the Planck and, I mean, Risa et al., and it can be also other things. What do you personally think? Where's the problem? Is there systematics in the H0 estimation, or?
Yeah, so no, that's a really interesting question. Part of the reason why I think it's the most interesting question or tension that exists is because sometimes the tension exists, but you're convinced that that thing must be wrong. I think this is pretty interesting because it's hard to say what's causing it. I used to be more skeptical of the direct H0 measurements, but I've heard some talks by people and talked to people, and there are these tails in the likelihood, but like as Hiranya showed, that reanalysis, it's still almost 3 sigma tension, even in taking those non-Gaussian pieces into account. So yeah, I mean, I think there either has to be some systematic issue, like I mentioned, somehow in the sound horizon, which seems crazy, or you could imagine one part of the local distance ladder being systematically off somehow, but they've really checked a lot of things in a variety of ways. So I don't know if Hiranya has a.
And anyone else has a strong opinion or semi-strong opinion? Eiichiro? Sorry.
Well, I think that we need more data of the types that we've got and independent data in order to check it. I completely agree with Ashley that the reason that people are more triggered by this tension than other tensions is that every element of possible systematics people have been thinking about has been checked very rigorously now. And this will continue to be checked, but it is something that hasn't gone away despite a lot of effort. I guess nobody actually mentioned, including me, that the Cepheid distance ladder measurement can additionally be checked through the Gaia parallax methods, and this has been now checked, and it's still consistent with their old measurement with small error bars.
Yeah, that was a big check, yeah.
I think we still need some consistency check of what Risa et al. Is doing as well. I mean, they are the only group which are coming with the H0 measurements, and I hope that there are some other independent group which can confirm these results.
I mean, it's not true that they're the only group that's doing that. So.
But do we have any other results, with the same precision as they do?
It's not the same precision, but the other distance ladder measurement groups agree with their measurement. I mean, they get a lot of Hubble time. Yeah. Yes.
I just wanted to make one more comment on this. I didn't mention that there is a DES result that combines BBN and BAO with the DES 3x2 point. So that has the nice feature that it's independent of both the supernova and the CMB entirely. That measurement agrees with the CMB. It's in, I would say, mild tension with the Risa et al. Data. So.
Yeah, it's basically this gray one, but strike out the Pantheon there, and yeah, it would have just been another Abbott et al. So. But yeah, that's a nice one to look at too.
Okay, let's.
If I can chime in on this, I'm here, back of the room. Here.
Okay.
Hi. Yeah, so I'm the speaker, one of the plenary tomorrow, and in my talk, I'll basically focus on measuring H0 with the gravitational waves and the prospects for that. We cannot solve this tomorrow, but I think it's safe to say that within a 5 years horizon, we can do a couple of % measurement of H0. And I'll stop here. No spoilers. Come tomorrow. You'll have the solutions.
Well, okay, we will listen to your talk, but I think my point was about the model-independent estimation of H0, which is something pretty much complicated and difficult. But
it's pretty. There is no model. I mean, we get the distance.
We will listen tomorrow.
That's it.
Yeah. Okay, so let's thank both speakers of the session. I think there is an announcement for the photo session.
Yeah. Everyone, please come up to the stage. We will have a conference photo now, and we will take one more in the just outside of the building after these photos. Okay, you please come up. And there's one change in the location, not the schedule, that this concert is supposed to be happening here before the conference dinner. Actually moved to the same place as the conference dinner. So we'll just come to the conference dinner place at 6:30, which is the other gate of the first floor of this building. Same building, but the other gate, not this one.